So hello guys, welcome back to my channel. Today we'll discuss about the three topic, that is the hydrolysis of XCF2, dipole moment of SiF4, XCF4, SF4 and BF3, and the optical activity of these four inorganic compound. So these three questions came in GATE 1995, and I think after watching this video you'll have some idea about dipole moment, optical activity of inorganic compounds, and the hydrolysis of XCF2, how it happens. So the first, I had already described the questions and will explain to you with detail. So first, the XCF2 and H2O. So hydrolysis reaction, that means H2O will come. So XCF2, if you see the oxidation states of Xc is +2 and fluorine is -1, and H2O, hydrogen is +1 and oxygen is -2. So Xc, which is an inert gas, so it will have a tendency to get reduced to its zero state, because it will it will have a tendency to reduce the oxidation state to +2 to 0. So where it will get the electron? So either it will get electron from fluorine or oxygen, but as fluorine is much more higher electronegative than oxygen, so Xc will get the electron from oxygen and the oxygen will oxidize to O2. So this oxidation reaction will take place where xenon will reduce to xenon chloride will reduce to xenon and H2 will be oxidized to O2. So this will be the product. Hydrolysis of XCF2 gives xenon and oxygen. So next, the dipole moment of SiF4, XCF4, SF4 and BF3. So the dipole moment comes due to the difference of electronegativity between when the two atoms are bonded. So we have to see the structural alignment of different bonds to get the final dipole moment of any molecule. So for XCF4, for SiF4, the silicon, which will have electronic configuration of 3s2 3p2. So silicon has 4 electrons in its outer orbital, and 4 fluorine will contribute 4 electrons. So total number of electrons will be 8. So electron pair will be 4. Now from VSEPR, valence shell electron pair repulsion theory, this 4 will be the bond pair, because 4 fluorine will be sigma bonded to silicon. So the 4 bond pair will be disposed as a tetrahedral geometry. So in tetrahedral geometry, the combined dipole moment of these 3 Si bond will be equal to the opposite SiF bond, and it will neutralize each other, so the dipole moment will be 0. Next, we'll come to XCF4. For Xc, the electronic configuration is 6s2 6p6. So xenon 8 electron in last orbital. So 4 fluorine will contribute 4 electrons. So total number of electrons will be 12. Electron pair will be 6. And out of this 6 electron pair, 4 will be the bond pair for 4 fluorine and 2 will be the lone pair. Now the disposition of this 6 electron pair will be like this. So the 2 lone pair will be in anti-position, and that is trans position, and 4 fluorine will be in equatorial position. And here the dipole moment of each bond will cancel each other. So the mu will be 0. Next we'll come to SF4. So for SF4, sulfur has an electronic configuration of 3s2 3p4. So last orbital will have 6 electrons, and 4 fluorine will contribute 4 electrons. So total number of electrons is 10. Electron pair is 5, and out of this 5, 4 will be bond pair and 1 will be lone pair. Now the 4 bond pair and 1 means 5 electron pair, so its disposition will be trigonal planar, but the lone pair will occupy in the equatorial position, and 2 fluorine will be occupy the axial position, and another 2 fluorine will be occupy the equatorial position. So ultimately it will be a seesaw structure, and here you can see that it will have a permanent dipole moment as it will not cancel each other. The opposite dipole moments will not cancel each other. So next we'll come to BF3. In BF3, the electronic configuration is 2s2 2p1. So boron last orbital electron will be 3, for 3 fluorine it will be 3, total number of electron will be 6, electron pair will be 3. For these 3, the geometry will be trigonal planar. So the one BF bond dipole moment will be cancelled to the combined dipole moment of these two another BF bond. So this will have mu equal to 0. So out of this 4 compound, only SF4 will have dipole moment. So we'll come to the next question. This question is about optical activity. So out of this 4 compound, which one will be optically active? So for optical activity, you have to see if the molecule contain any sigma plane of symmetry, center of symmetry, or axis of symmetry. So we have to determine the geometry, and then we have to see for these 3 symmetry element. So first one is PTNH3 whole 2 Cl2. So for this compound will have 2 isomers, cis and trans. This is the trans one, and in this trans one there is sigma plane of symmetry. As in molecular plane there is a sigma plane of symmetry, and also this Cl PTCl bond there is a plane of symmetry, and this NH3 PTNH3 bond there is a plane of symmetry, and also it will have center of symmetry, and also it will have C2 axis of symmetry, so it will not be optically active. And similarly, this is the cis isomer. So for the cis isomer also, this is C2 axis of symmetry, and also it will have a plane of symmetry, molecular plane, and also there is a plane between this this NH3 PTNH3 angle, by bifurcating this angle. So this will also be optically inactive. Now let me open the whiteboard. Sorry. There is another. Yeah. So next is NiCO over 2 PPH3 whole 2. Now this is tetrahedral geometry, and you can see here that it will be optically inactive as there is a plane of symmetry. If you can consider the plane CO NiCO bond, the plane which contain in 2 NiCO bonds. Next we'll come to the trans COEN2 Cl2. So if you see the trans CO this compound, there is a molecular plane of symmetry. No molecular plane of symmetry, but one plane of symmetry is there, and also C2 axis of symmetry is there. So this will be optically inactive. And last, cis COEN2 Cl2. This will have no Ci, Cn and sigma. So this compound will be optically active. So guys, I think you have some idea, you got some idea about the optical activity of inorganic compound, dipole moment, and the hydrolysis of XCF2. Guys, if you have any doubt regarding this video, please let me know in comment box, and I will happy to help you. Thank you. Have a good day.